Good morning. It is my great pleasure to be here to join the celebration of 50 years of Aharonov-Bohm effect. In the next 30 minutes or so, I'd like to present our work on pairing symmetry in high-temperature superconductors, in Cuprates, and in the recently discovered iron Pnictides. As you know, there's a new important member added to the growing high-temperature superconductor family. Now here is the it's very hard to. Here's the formula, and as an example, lanthanum, iron, arsenic, oxygen, fluorine. It's doping with fluorine. Fluorine here with TC 26 degree K. That was discovered a little bit over a year ago, and that caused a lot of interest. And scientists at Chinese Academy of Sciences, Beijing, China, they replaced this rare earth by other rare earth, lanthanum by other rare earth elements, such as samarium and neodymium. They managed to get the TC up to 55 degree K. So this kind of remarkable discovery of iron, high-temperature superconductivity in iron-based superconductors really challenged the existing paradigm of high-temperature superconductivity. That is because they are characterized by complex Fermi surface topology and small electron correlation, unlike the Cuprate superconductors. So one of the most important steps to understand superconductivity in iron pnictide is to elucidate the nature of pairing, in particular pairing symmetry. So this requires us to do a phase-sensitive symmetry experiment. And we do have some very new results on the symmetry of all this iron arsenic-based superconductors. Now, before I present that, let me just take a few minutes to talk about phase-sensitive experiment that we did in the Cuprates, just to set the stage for later presentation of the new results. Well, phase-sensitive experiment is based on two macroscopic quantum phenomena, namely Josephson pair tunneling and flux quantization. Here's the Josephson expression for supercurrent. And if you make a junction out of unconventional superconductor, namely non-S-wave superconductor, then it is possible to have a junction that will give you a negative supercurrent. What that means is if you absorb this negative sign in the sign function, that will give you a pi phase shift. Now here is nothing more than the requirement of a macroscopic pair wave function to be single valued as you go around a loop of 2 pi. So when you calculate the energy, then you will find you work with a superconducting loop containing Josephson junctions. All you have to do is just count the number of side chains in supercurrent. If it's an even number of side chains, then you get a net phase of 0 or 2 pi. And that leads to regular integer flux quantization, as I indicated here. Now, if the sign change is odd number, then you get a net phase change of pi. that would lead, the system would be frustrated and it wants to compensate the energy, the Josephson junction, as you put a pi in here. And that will cause the system to spontaneously generate a current. That produces a half-flux quantum. Here you have a plus, minus half-flux quantum threading in the loop. And this is a doubly degenerate, time-reversed ground state of the pi loop. And that corresponds to the supercurrent flowing in the ring clockwise, counterclockwise. The energy is the same. Now, as a function of the loop geometry, then one can use the presence and the absence of a half-flux quantum effect for probing the phase of the order parameter, in this case, energy gap, as a function of K. In the past, there are several techniques developed for observing the half-flux quantum effect. Let me concentrate our own experiment we call the tricrystal experiment. I designed this experiment with a substrate consists of 3 crystals specifically oriented is such that if it's a D wave, and if you pattern a high TC film, a ring on it, then at the tricrystal point, it has 3 junctions and the change sign once. Therefore, if it's a D wave, like I showed here, it should show half-flux quantum at the center ring, but not the other ring. The other ring just the control of my experiment. And indeed, we were very, very happy. I remember when we first found this using a scanning squid microscope. Here shows the image of a scanning squid microscope. And here's in the center, you see the forget about it. You see the center. There's some signal. We calibrated. Indeed, that's a half-flux quantum. And then after that's established, then you don't need to do the patterning. The patterning is kind of hard, especially make a ring right at the center of the tricrystal meeting point. Now what you do is you just deposit film. And using a scanning squid microscope, look at the vortexes. And you see at the center, there's a small vortex in there. That's a half-flux quantum at the tricrystal. That's where it's supposed to be, if it's a D wave. And then you see the Josephson vortex along the boundaries. See, outline the boundary like this and that. And there are epicausal vortex in the gray. They're all single flux quantum, except the one, the meeting point is a half. So this represents strong evidence for D wave in Cuprates superconductors. Now I want to mention that when I designed this experiment, I took into account the junction interface, the grand boundary junction interface may not be ideal. So I used the formula of a Segrest-Rice clean limit as well as the formula I developed for maximum disorder. So in other words, this design is a foolproof. Regardless how bad is the junction interface, as long as you have a supercurrent flowing, you will get half-flux quantum if it's a D wave. So, so this really is a yes or no period-symmetry test. Very definitive test. And for those who are interested in more details, we have a review article. You want to take a look? Okay, now let's get to the presentation of our new results, the phase-sensitive experiment for definitive determination of order parameter symmetry in iron pnictide. This is based on unpublished work entitled integer and a half-integer flux quantization transition in a niobium polycrystalline iron pnictide loop. And here's my co-workers. And especially I want to mention Chang C Tsuei. She's my postdoc. And she did a lot of work on this, made an important contribution to all aspects of the work. And the sample, the high-quality polycrystalline sample, was provided by Ren and Zhao from Chinese Academy of Science, Beijing, China. Okay, what is the difference between the cuprate and iron pnictide? Basically, it's the band structure. In the iron pnictide, the band structure derived from the iron d orbitals, as I indicated here. And sure enough, the photoemission result indicates indeed you have multiple Fermi surface sheets. In the center, you have this whole pocket, and then outside you have the electron pocket. So totally 5 Fermi surface sheet. And this is in contrast to this single band physics involved in the cuprate. That you have only one single band. So that's quite different between those two systems. And as a result of this, it's very interesting. So the Fermi surface is very complicated. Of course, that leads to complication in determining the parent symmetry. Now, the theoretical predictions about the parent symmetry, based on spin fluctuation models, people say that it could be S plus minus. In other words, if you have a paired coupling process going like this from one Fermi surface sheet to another, and that will give you the so-called S plus minus. In other words, each Fermi surface sheet is S wave, but in between those two Fermis, it changes sign. So that's why if one's plus, the other one's minus. So that's why it's called S plus minus. And it could be D wave. And it even could be pure S wave, the regular S wave. And there are other theories that says it could be P wave. So we got to do experiment to detect the sign change if it's S plus minus. Okay. Now the current status right now is there's lots of experiments. They are trying to figure out what is the parent symmetry in these new materials. However, most experiments are amplitude sensitive. In other words, it's making measurement of the pair wave function is amplitude, not phase. So that's why it's model dependent. It's difficult to pin down unambiguously what is the parent symmetry. So you got to use a phase sensitive experiment. So that's what I'm here trying to present. And here, I want to mention the challenge in designing such a phase sensitive experiment. The reason why is this. First of all, we don't have the high quality material. We don't have a large high quality crystal, single crystal. We don't have epitaxial films, high quality epitaxial film. That makes it very, very difficult to do an experiment. And furthermore, the Fermi surface structure is so complicated that makes it even worse. And let's recall the early days when we did the D-wave experiment. For instance, here, if you have a D-wave material like this, and then make a corner junction using S-wave like a niobium, which is a singular even parity regular S-wave superconductor. Then you see you have a you go from this direction, the current goes this direction, so plus to plus. But you go the other direction, it's minus to plus. So as you circle around the current, supercurrent circle around this corner, what do you get? You get a sign change once. So you expect there will be a half-flux one here. And that's indeed the case. So it's relatively easy because there is a one-to-one from K dependence, K representation to R representation. So you can design an experiment like this with relative ease. Here it just shows one example which we published a paper in Nature year 2003. You see, again here, there's the corner junctions. The corner junction will give you the half-flux quantum effect, and that you show as the zigzag pattern of a half-flux quantum. One is up, down, because they antiferromagnetic coupled. So that's what you get. Now, in this case here, it's very, very difficult. If it's S plus minus, there is no apparent symmetry breaking that you can use in designing the experiment. So that's a very, very difficult experiment to do. So our approach is this. We try to establish a macroscopic quantum coherence across interface, the singular pairing, niobium and neodymium. This is the iron pnictide. We want to first observe supercurrent. Then we want to see flux quantization. Remember, flux quantization is finite, h over 2e. That's a very, very small number. You got to do a very good experiment in order to see it. You got to do experiment in a low noise environment with a very sensitive instrument to see that. So here's our experiment setup. So what we have is a niobium loop here interrupted by polycrystalline material, neodymium 1111. That's the arsenic pnictide. And here, there's a two-point point contact junction here. And notice we have a copper beryllium springs loaded against it. So we can adjust the contact strength by adjust the spring strength. Okay, here's a toroidal coil that we use to apply magnetic field into the niobium ring. And yesterday in the talk, several people mentioned the toroidal coil. Now you got it. Okay, now this is the pickup coil for the squid, using squid to monitoring the magnetic flux state in the ring. Now here is what we call the electromagnetic excitation device to input some electromagnetic disturbance pulses in order to induce the flux change in the niobium. Here's the results. See, as you increased the field, see here's the loop with the magnetic field in it. And as you apply the flux, the system develop a diamagnetic response. So you get a supercurrent going up and up with the magnetic field until it reaches a sort of critical value, critical current. And then what happens is that it will let flux come in or out. And here's that's why you see the zigzag. That indicates that the flux start coming in and out the ring. Now, if you adjust the coupling strength appropriately, low contact, and then what happens is you see you can even resolve single flux quantum. The red bar represents a single flux quantum. Okay, the blue one means a bundle of flux coming in. So that's the applied magnetic field. Now let's do another experiment. Let's not apply magnetic field. Just start with, you prepare the system with some flux in it. Then you turn on this electromagnetic device here. This is not a sophisticated device. Basically, it's a hair dryer that I put it in the other side of the lab. I turn the switch up and down. The noise will get into the magnetic shear room, and the system is so sensitive would detect that. And that caused the magnetic flux change. Okay, so what do you get? You get a flux, single flux jump, and multiple flux change. But they're all integer, finite, in terms of multiple units of finite. So just with this, we can say something about the parity of the new material. Because we observe macroscopic quantum coherence through the diamagnetic supercurrent and also through the flux quantization. And the niobium is a spin singlet, even parity material. So it has to be singlet. So right there, we rule out P wave. Okay, now the next step is to do the same experiment, but think about it. Since we use a polycrystalline material, the polycrystalline material, you can have a different flow pattern of the supercurrent. And that supercurrent corresponds to, in terms of the energy landscape, that means different energies. So when you zap with the electromagnetic pulse, it will maybe the current flow, the main current flow, will jump from one to another. One maybe contains no pi junction. The other one may have pi junction along the way. So that will give you what? Give you a half-integer flux. Remember, if you stay on one path, then you cause this magnetic flux jump. That will only give you integer flux. You got to switch the path in order to see the half flux. Okay. And indeed, after we manipulate the experimental parameter, we see half now. Now, the dotted line means the middle of integer of flux quantum. So you see the jump, now you see half, 2 half, 3 half, and so on. In addition, you have integer. Okay, here's a summary of a result as a function of coupling strength. And since we observe hundreds of such a quantum flux quantum transition, so let's plot histogram to see. When the current is like this, you have only the integer flux jump. Now, when you increase the current, you push the point contact a little bit harder, then you start to see the half flux quantum. Push more, you get more. But clearly, you see there's two distribution profiles. In other words, they're different. They're not just one story. There are two things. And that's consistent with the thing I just discussed. You need to see half-flux quantization. You need to switch paths. So that just shows the red and the blue here represent two different paths. So it's highly suggestive, but I don't have a hard proof of it. Okay. Now people will start worrying, especially my postdoc, will worry about, could it be this is an artifact? Could be something else. So we try to rule out all the other possibilities. I don't have time to do them. Oh, yeah, one thing I want to mention, this experiment setup is very nice. You could just pull out the polycrystalline material, put niobium back in, and that, nothing weird will happen. You should see single flux. We never saw any half flux. So that's a very, very reassuring. The thing we saw that was really genuine. So the half flux quantum jump really is not artifact. Okay, now with this, we're in a position to say something. Let's say, since we non-zero finite Josephson current, we say it's a spin singlet. Half-flux quantum told us there's a sign change now in the current, in the supercurrent, flow through the sample. And then we rely on other people's work published in the literature. I do not have I cited it here. And they clearly show it's not D-wave. So if you use that to rule out D-wave, then our experiment represents first definitive experimental evidence to show the new superconductor is S plus minus. Then if you are interested in it, you can find out what are the possible source of a pi junction in this experimental setup. We say there are two possibilities. One is at the niobium iron pnictide interface. In other words, this is the point contact right at the contact. The other thing is in between the contact. There are polycrystalline material. You could have a sign change over there. So those are the two possibilities. And in the literature already, there are some papers discussed about such possibilities. Okay, conclusion. So we observe macroscopic quantum coherence across niobium neodymium 111 junction interface. We observe diamagnetic supercurrent. We observe quantized flux jump. And in particular, we observe new half-Joule quantum effect. And all this leads to the conclusion the new material is a singlet pairing, even parity, and S plus minus pairing symmetry. Okay, let me, how much time do I have? 5? What?
5 more questions.
Oh, let me just quickly finish it, okay? We know there's a sign change. So in other words, the gap function has a sign change. If you put this into a BCS gap equation, now with knowing that this has a sign change, now how to solve this V? V is the pairing potential. Okay, then you have to conclude the potential has to be something like this. In other words, here's a relative small q, V as a function of momentum transfer, the small q. This has to be attractive, relatively attractive. It can be, the whole thing can be repulsive, but this has to be relatively less repulsive. And here's repulsive in this case. Now, in the iron pnictide, let's say we assume a simplest case, you have a two band, another two Fermi surface. Okay, then you get the same conclusion. The sign should be reversed. So that's consistent with S plus minus. So the constraint on high temperature superconductor pairing mechanism, this is what we really want to get a handle on it. The basic message is to say that the pairing interaction has to be large Q, be repulsive, small q attractive. This is applied for both D wave and S plus minus symmetry. Turns out they give you the same requirement. Now, what are the possible high temperature superconductivity mechanisms? I would say this has to be if it's an electron phonon, has to be unconventional. Why? Because there is some theoretical calculation indicates that the electron phonon coupling, a regular electron phonon, just simply does not support high TC in this system. So if anything, it has to be a specialized phonon, anharmonic, nonlinear coupling, and so on. I did some work along these lines recently. The other things, obviously, is spin fluctuation mediated pairing. That will automatically lead to S plus minus. Then the other things is possible a combination of 1 and 2. 1 and 2. Now, in the case of a cuprate, maybe one is more dominant. In the case of iron pnictide, maybe 2 is more dominant because the presence of iron magnetic lattice in the system. So with that, let me conclude my talk. Let me thank my co-workers, especially John Curley. He worked closely with me, and he did all the scanning squid microscope measurements, and other colleagues. And more recently, this is my co-workers on the new experiments. Okay, so let me stop here. Let me thank you for your attention. You want to ask a question about my picture here? Yeah. Okay. See, here it shows that I'm standing on a strong magnet. And that's floating above YBCO, the high temperature superconductor. And so that's why I said I was levitated by a strong magnet above a superconducting YBCO disk. Now here's the disk. That's the magnet. I was standing there, And you can test. You can run a rope behind it, and nothing, just like magic. And people can rotate, spin around. And so I was really floating in the air. Now, you see here, in the background is liquid nitrogen tank. So it is my sincere wish. We work hard enough. If we get the high temperature superconducting mechanism, that will lead to the discovery of even more higher TC material. Hopefully, we can get room temperature superconductor. Now you don't need the liquid nitrogen here. Maybe all you need is just cold water. Okay, so that's it.
You didn't say anything about. Thank you. You didn't say anything about the magnetic state above the superconducting the transition. Are these antiferromagnets?
Yeah, broadly speaking, it is antiferromagnet, but this material is an implant magnetic structure, collinear spin goes like this.
Right. So the antiferromagnetism persists below the transition temperature?
Yes.
And you know that?
It's doping dependent.
Doping dependent. And you know that by the samples are big enough that you have neutron diffraction data on them?
Yeah, there's some I didn't do, there in the literature, lots of data.
Okay.
Neutron scattering and other measurements.
Okay, thank you. Thank you.
Okay, is there an urgent question? Okay, so let's thank Dr. Tsui again for his talk.